RACO webinar this morning. My name's Tom. I'm with RACO, and leading our webinar on ultrasonic flow measurement today is going to be Lorenzo Nirchi from GE Measurement and Control. Lorenzo is their national account manager and also is a flow product specialist. He's been with GE for 20, how many years now?
Almost 16 years.
16 years now. And Lorenzo is also a former employee of RACO, worked for RACO back in the 90s. So we're glad to have him back and helping us out here. If you have any questions during the webinar, there's actually a little section on the bottom called questions, a little tab there. Feel free to type anything in during the presentation, and we'll get to those at the end of our presentation. It should be about 30-35 minutes, and we'll have a little time for Q&A and any other discussion. Also, we'll be recording the webinar and be making it available at raco.com at a later date. So if you missed out or you dialed in late, you'll still be able to see everything that was presented. So without further ado, I'm going to pass it over to Lorenzo and go from there. So thanks so much for joining us, and the floor is yours.
All right. Good morning. Let me move the phone so I can make sure you can hear me. So we're going to go through just the basics of ultrasonic flow meters. This is we intended this to be very basic, kind of a 101 type course, and with the hope that we'll continue to do these and move into more technical type discussions at a later date, and with your feedback, maybe even particular application type discussions. So we'll get moving here. So what we're going to go through is just the introduction of ultrasonic flow measurement. What is the ultrasonics, the waves? How do the transducers work? The difference between the Doppler and the transit time? Typical hardware that you would use in an installation. And then we're going to go through installation considerations. The fluid dynamics, required straight runs, traverses. I'll discuss what an actual traverse is, and clamp-on versus wetted systems. So what are ultrasonic waves? It's a frequency, and they're typically classified in three different classes: subsonic, audio, and ultrasonic. Audio is where we could hear things. Ultrasonic is where we're working, and subsonic is what we can't hear. I think elephants can hear that. We actually have a slide that shows an elephant that can hear that. But we're working down in the ultrasonic range. Right. The speed of sound is the main measurement that we're making through a given fluid or gas. And basically what that is how fast the waves moves through that medium. In gases, it's a little slower. In liquids, it's a little faster, and it's really got to do with density. The higher the density, the faster the sound speed. So the actual transducer is nothing more than really a piezoelectric crystal that we energize and turn into mechanical energy, which is the wave itself, that then travels through the fluid to the receiving transducer. We clock how long that takes to happen, and we send a wave, actually a series of waves back to the upstream transducer. So these transducers are senders and receivers. So in essence, it's like us talking back and forth on a phone call and clocking how long it takes for those signals or our voices to carry that distance. Right. Some of the benefits of ultrasonics is there is no pressure drop, regardless of whether it's a clamp-on or a wetted system. There's really no pressure drop to speak of. There's no moving parts, so maintenance is very low on these types of meters. Large turn-down ratio, we'll show that later, but typically in liquids you're looking at 40-to-1 turn-down, and in gases you're looking at 150-to-1 turn-down. In flare applications, if any of you get into that, you're looking at a high end of 385 feet per second down to 1 foot per second. Our detectable range is actually down to 0.1 feet per second, though. The accuracy starts to fall off a little bit, but we do read well below 1 foot per second. Again, we can do clamp-on or wetted systems, and we can do gases or liquids. All right. So like I had mentioned, the transducer is both a transmitter and a receiver, and they're looking at just the ultrasonic pulses that the piezoelectric crystal is making for them. The transit time is how long it takes for that signal to travel from, say, the upstream to the downstream transducer, and then from the downstream back up. If you've got velocity, I like this screen, but I like to say it more in layman's terms. If you've got zero flow in your pipe and it's just full of water, the upstream to downstream signal travel time should be the same as the downstream back up. There's really nothing in there making it go faster or slower. As the velocity increases, your T up is going to be faster, and your T down is going to be slower because it's got to fight that velocity. The time difference is proportional to velocity. Once we have the velocity and we've already programmed the meter for the specific pipe, we know the ID, so we then calculate for volumetric flow. In gases, we then take in temperature and pressure, and we can give you calculated mass flow, standard cubic feet per minute per hour, whatever units you're looking for. Again, the technique, just another page that kind of goes over what exactly we're doing. So if you like calculations, this is a great page to look at. But basically, the biggest things that we look at is the acoustic path there toward the bottom through the fluid, how long that is. And then the axial projected path, which is the length of that path. A lot of times that's very close to the actual ID of the pipe. And then, of course, the path angle. You don't have to worry about the path angle. That, when you program the meter, it tells you where to put the transducers. You put them there, and the meter does what it's supposed to do. We don't really get into moving the transducers back and forth to try to find a sweet spot, because in my mind, I think you're just cheating the meter at that point because it doesn't really know where the transducers are. Right? So how does Doppler work in comparison? So Doppler is a little bit different, and it likes to work in dirtier fluids. A lot of times I remember going through the industry, we would actually supply bubbler systems to help a Doppler work, just so it has something to kind of reflect the signal back to the receiver. And typically those transducers were already set side by side. You didn't have an upstream and a downstream. And you're basically just looking at a shift. You're looking at how fast all these particles are moving, and hoping that that flow is representative of how fast the bubbles or the particles are moving through that stream. It wasn't always the case. Doppler isn't quite as accurate, but in applications where you're stuck with nothing else but that, it can at least give you a measurement, and they're still available today. All right, so basically the technique, the problems of scatter size, the scatter reflectability, the scatter velocity, clean fluids, obviously you can't do it, and typically that accuracy was somewhere around 10%. And it is really because you could have the bubbles or particles actually spinning around doing things that really aren't conducive to what the actual velocity of the flow is doing. So you couldn't really depend on it being that accurate. So if we look at some of the comparisons, transit time is pretty versatile. We can deal with gases, we can deal with liquids, steam, clean and dirty, and it's a lot more accurate. Typically a clamp-on system can be 1% accuracy. That's very, very achievable. And in inline applications, easily 0.5%. In our custody transfer type meters, we're looking at 0.15% type accuracies. And with Doppler, they couldn't do gases. They were just dirty liquids only. They had to have that liquid, or that dirty liquid to actually operate correctly. So reasons for using ultrasonics. We're going to go through the ranges, the wide range of pipe sizes. We've done everything from a 1/2 inch to 200 inch. I personally have gone up to a 108-inch pipe. Turn down ratios, 0.1 to 40 feet per second in liquids. In gases, it's 0.1 to 150 feet per second. Again, no pressure drop. Bidirectional flow. This is important in a lot of places. I never really knew it until I started dealing with ultrasonics. There are areas, especially in campus-type environments, where they want to be able to see the flow moving forward or backward. There's no moving parts, and clamp-on is independent of pipe size. So the same meter that's going to fit on a 2-inch pipe will fit on a 200-inch pipe for the same cost. It doesn't change. The transducer frequency might change. We have a couple that we use, but you don't have to change them in between. You just use one or the other, and we just know it by application. Typically, anything under 14 inch, it's a 1 megahertz transducer. Anything above that can go to a half megahertz transducer, and it's really that simple. Some of the reasons for using ultrasonics. Being on the outside of the pipe, we can deal with corrosive fluids. We don't have to worry about what the instrument is made of because it'll be in contact with some corrosive fluid. High temperatures and high pressure gases, we can deal with those. Truthfully, actually clamp on or wetted these days. Radioactive fluids, multi-channel capability. A lot of our meters are 2-channel meters. That can be used as 2 separate flow meters out of the same box, or if you don't have the piping that you typically would need, 10 and 5 in liquids, we could actually use both of those channels to traverse the pipe twice and actually average those 2 signals together and give us an averaged flow measurement, which is sometimes a bit more accurate. And then cost of installation is very low on clamp-on because we're just clamping onto the outside of a pipe. We're really not bothering anybody. It might take, literally for me, on a portable meter, it might take 5 to 10 minutes to have a measurement. Of course, we have to worry about, how are we going to get power there for a fixed installation, but the installation on the pipe is certainly a lot quicker. Some of the components of an ultrasonic flow meter. In a wetted application, we have the electronics, which could be portable, dedicated. It can be an explosion-proof transmitter or even multi-channel. And then we have transducers, and you see those on the pipe, and a cable that interconnects those transducers to the electronics. In a clamp-on, it's much the same, but you don't have transducers that are actually inside the pipe. So you have just transducers that are clamped to the outside of the pipe. The adder here is the couplant for the transducer. When you put a transducer through the pipe, the couplant makes sure that the signal is actually going into the pipe and not escaping into the air outside. And these days, I know in the past, couplants were always probably the biggest thing that somebody would complain about because they were either water-based or even some silicone, but over time they would deteriorate, dry out, and the meter would most typically show a sound speed error. These days we're using solid couplants that last 10, 15, 20 years. They just kind of stay on there. Right. In gas systems, the components a little bit different for this one because you still have transducers. You can see the transducers here. We have the pressure and the temperature transmitters, and we have the actual electronics. In this case, this is a flare meter, but the actual components are the same regardless of what type of gas you're doing. But what we add is a preamplifier within 10 feet of the transducers, and the reason for that is gases are very noisy. So we take the signal off the transducers and we amplify that good signal to move that back to the electronics. And we do that within 10 feet of those transducers before it deteriorates too much for us. And past those electronics, we typically can go out 500 to 1,000 feet or less. But we typically custom make those cables for you to whatever length you need. So some fluid dynamics, flow profile, Reynolds number. Reynolds number is a measure of the shape of the flow profile. It's really not a number that you need to change. The meter kind of determines it, but it's good to know. The flow profile is the shape of the flow due to the friction and the viscous forces in the pipe. And we'll actually have some pictures here. All right, so there's three different profile regions. There's laminar flow, there's transitional flow, and there's turbulent flow. And they each have their range of Reynolds number. We work very well in the laminar and turbulent regime. We don't do very well in transitional because it's undefined. It's very difficult to make a measurement. You don't know where the actual velocity or flow profile is inside that pipe. So it makes it a bit more difficult. Can we get a number? Typically, yes, but it may not be a 1% number. Straight run requirements. Typically in liquid applications, regardless of whether or not it's clamp-on or wetted, we're looking for 10 pipe diameters upstream of undisturbed flow and 5 diameters downstream of undisturbed flow. In horizontal, vertical flowing, we can do horizontal flowing. We can do vertical flowing up. If you don't have the 15 diameters that are required, the general rule of thumb is to split it in thirds. Take 2/3 of that pipe run upstream and 1/3 of the pipe run downstream. Or we could even go with multi-path. We talked about multi-channel flow meters, where we actually take two measurements on that same section of pipe to give us a bit better accuracy. Flow straighteners can be installed, but that kind of takes away from the whole clamp-on thing. And accuracy can't be quantified as well when we have less than 10 and 5. And the repeatability suffers a bit also. Again, pipe ranges are 1/2 inch to 200 inch OD. You see a couple pictures of some relatively large pipes. In the larger pipes, especially with portable applications, if you look at that lower picture, we actually have magnetic clamping fixtures that allow you to get those transducers on the pipe relatively quickly so that you can get them on, make your measurement, and then get back off. In permanent applications, we would actually affix a clamping fixture to that pipe held on by a stainless steel band. Okay. Other considerations, and just a couple pictures of good locations and bad locations. Obviously, the one on the left, nice long runs, lots of pipe to work with. Those are great locations for us, or for really many meter types. Bad locations, shown on the right, lots of valves, bends, flanges, what have you. It's all there. Very difficult to put a flow meter in it, and although you can usually get a measurement, it's hard to quantify what the accuracy of that measurement is going to be. All right. We'll talk about the traverses now. I mentioned that a couple times already. Typically, for tough applications, or larger pipes, old pipes, dirty fluids, gases and steam, we need more signal. We want to do a single traverse. And what that means is we're going through the pipe one time, which is here. So the transducers are basically mounted on the pipe. In this case, it's showing it on top and bottom just so you can see both. Typically, we always mount on the sides of the pipe someplace, especially in liquids. That's a single traverse application. It's a little less signal. It's certainly less path, but it works well. The larger the pipe, the more path you have, and the more resolution you have. In the shorter pipe, in the smaller pipes, that's not as true. But in demanding applications, in old pipes, that we sometimes have to do that. And what I mean by that is old pipes that might have a lot of scaling built up inside the pipe, or maybe a lot of rust and bubbled up paint on the outside of the pipe. Mentioning the outside of the pipe, if you have bubbled up paint or loose rusty areas of the pipe, we don't need to get down to bare metal. You don't have to sand that thing down until you see this nice shiny pipe, but we do need a nice smooth area without any air entrapped underneath bubbled area. So if you take a small wire brush to it and clean off the area, that is 9 times out of 10 more than enough for us. Multiple traverse. So typically we're either 1 traverse or 2 traverse. This is a 2 traverse example. And basically what that means is the transducers are a bit further apart. The signal moves into the pipe, bounces off the back wall of the pipe, and then back up to the receiving transducer. It gives you a bit better accuracy. It gives you a little less signal strength, but it's usually more than enough for us. But you do get a lot better accuracy because we're traversing that pipe twice now instead of just once. You don't have to worry about the double or single traverse. In the programming of the meter, when we tell it that it's going to be a single or double traverse, it'll tell us how far to place those transducers apart from each other. So it's not something where you need to do a whole lot of guessing. And the clamping fixture itself actually has a scale on it. So once you set that scale, you clamp the clamping fixture here at the bottom onto the pipe, and then you install the transducers, and then wire the transducers to the electronics. In wetted systems, we use a flow cell, and they can be either hot tapped or cold tapped. Shutdown obviously is required because we have to install it. Certainly more accurate. Actually, this is probably kind of old. Typically within 1% if we don't calibrate the flow cell, but if we actually calibrate the flow cell, which we do most often now, typical accuracies are at 0.5% or better, which goes where we say it can be calibrated or validated. And we can deal with extreme temperatures. The nice thing that I like about this is this piece right here, which is called a pan adapter. It's basically, if you can think of it as a high-end acoustic thermal well. That goes in before the transducer. Here's a plug, and the transducer is behind it. What that does is it isolates us from the process. So once this spool piece is actually put in the process, the plugs are in. If anything ever happened to the transducer, somebody bumped into it, bent the head, broke the head off, broke a cable off, and the transducer needs to be replaced, we can easily pull that transducer off of the plug and put it back in. There's no pass-through from the pen adapter through to the transducer. It's a solid buffer. And I like it for that reason, probably more than anything else, just because you don't have to shut your process down. We all know how difficult it is to shut a process down and have to deal with that. So being able to stay away from it is actually a really good feature. Okay, and obviously in clamp-on there is no shutdown required. There's no leak points to worry about because there's no flanges or anything else to deal with. The installation is obviously much easier. You can change the configuration anytime. You can move it if you need to use the clamp-on meter someplace else in an emergency. It's easily removed and put someplace else. And we say the accuracy here, and this slide is actually old, I apologize, within 2% of reading. Most of our new literature all says 1% or better. And that's it. How do we do on time? 25 minutes.
Pretty good.
Not bad. Not bad. Now, do we have any questions?
Yeah, we'll open it up again. If you do, please type it into the question tab on the right hand of your screen. It should be in that little like orange box. You can address any questions, concerns that you have.
What you'd like to see eventually. If you didn't like what I did, I can take criticism pretty well. Plus, they shut the door here, so
right,
I'll be okay.
Question about temperature limits for sensors.
Okay, so temperature, we have a couple different sensors that we use. Most normal, our normal temperature sensors are somewhere in the 240-degree range, and then we can get above that with higher temperature up into the almost 500-degree range. Using the pan adapter that we talked about in the slide, and let me see if I can move back on the slide here. Well, why can't I move back? So we make this this plug here. It can actually be made in a BWT system. You don't need to really worry about what that is, but they can be made in different lanes, and we move those back to kind of dissipate that heat before it gets to the transducer that can be damaged. And with that, we can certainly get up to temperatures that are 750 and even beyond that temperature range. Some very high temperature applications.
Clamp on be used in steam flow measurement?
It can, and we've done it. We don't do a lot of it, mainly because we have to make sure the steam is clean, but the biggest part is getting that clamp-on sensor onto the pipe. And remember how I talked about having the couplant that goes between the transducer and the pipe. When you're dealing with a hot pipe like that, the couplant that we put on, and we have one that can go onto the pipe, it's not a problem, but it does smoke a little bit until it cures. It kind of cures and becomes kind of a rubber material. It can peel off the pipe, but during that time, there's EHS issues. You have to make sure that you've got sufficient clean air, or enough in an area where that's not going to be a bother to you or anybody else in a building. So there's that kind of consideration, but it can be done, and we have done it. Good question.
So as a follow-up, so this is for flow cell only?
For
I think the follow-up to temperature possibly.
So, well, I'll go for it first. So we can do clamp-on or flow cells for gases or liquids. The temperatures we can deal with on a clamp-on, we're kind of limited to, well, actually we're not, because we have high-temperature clamp-on. And we'll get into that in additional webinars, actual equipment and some specific applications. But we have clamp-on transducers that can hit the 700-degree mark and over. And we have wetted systems that can do the same thing. Did that answer your question? I hope. Yes. Thank you.
Well, it seems to be the end of the questions that we have coming in. So we thank you for taking the time, joining us. Again, this will be available later date at RACO.com. Also, be sure to look at our RACO.com training page to let you know for upcoming webinars that we have coming up available. If there are other topics, we'll be sending out a follow-up email if there's we want to dig into the flow technology a little bit more specifics. Please let us know. We're always looking for topics or areas that are going to be of most interest, to our customers. So, again, Lorenzo, thanks so much for leading us today, and appreciate everyone's time. And everyone have a great day.
Thank you.